So my session for today is about iterators. I would like to spend an hour or so, depending on the number of questions that you have, an hour or so on this topic and tell you what's new in Rust 153, which came out a few weeks ago. And I would like to take this opportunity to dive deeper into iterators. Iterators, let me quickly shut down this one here. So now it's good. Iterators are interesting. Iterators are very interesting. I know them from various languages that I use, TypeScript, C#, and so on. And when I learned Rust, iterators were one of the first things that I was really interested in. So I took a close look, and for me, it was rather surprising that it took Rust so long to be able to just iterate over a bunch of, for instance, numbers in an array. And this will be the main part of my talk today. I would like to talk about iterators, especially in conjunction with arrays. And I would like to dive in some very important Rust properties that are the reason why it took relatively long for us to learn these tricks for iterators and arrays. If you want to ask any questions, if something is new to you, if I'm too fast or too slow, give me feedback, ask questions by using the chat window in YouTube, or you can also ask questions in Discord. I will take a look at questions on the Discord server after my talk. So now let me share my screen with you. Here you see the storybook. It's just a quick gathering of notes, what I would like to walk you through today. So if you find some code snippets interesting, you can take a look at this URL and copy them out. Everything else will be done live. Okay, with that, let's dive right into it. The first thing that I would like to show you is I would like to show you the old version of Rust 1.52 and show you what we had, what problems we had there. So let me quickly, oops, sorry, wrong one. Now we are ready. Let me quickly run a Docker container with Rust 152, okay? Okay, here it is. Let's go into Visual Studio Code and open up Visual Studio Code within this Docker container. So now I am in Visual Studio Code connected to this Docker container, and let me quickly here install the Rust analyzer here. Yeah, okay, it's already installed in this Docker container. That's fine. That's good. I just broke that one. So okay, let's go here. Create a directory. Rust demo, here we are, and open this folder up here in my Docker container. So open a folder, and here we are. That's good. This demo broke. So let's reopen this one here. Maybe it works at the second try again. Start. Now it looks much better, I think. Yes, much better. Here we are. And now I think I can also, yes, check the language server is installed. Everything is fine. We are good to go. Sorry for the quick glitch. I had some problem connecting Visual Studio to my Docker container, but now it seems to work. Let me quickly start a new demo here with cargo new. Here we are, and open up the code here. Looks good. Everything is fine. Okay. So if we quickly type in some code here, let me do that. For instance, let's define some numbers here, and let's do them something like this. This is just a numbers array, nothing special. So in the good old times, prior to 153, I had a problem when trying to do the following. Here we are. And if I want to say, for instance, print line, something like this, and something like this, print the numbers, something like this, I had a problem. This doesn't work, or this didn't work, because an array with a fixed size of 5 did not implement the proper traits up to Rust 152. This changed in 153. What you could do in Rust 152 is I could change here, that one, to a reference, and that brought me, you see it here, a reference to the numbers. So I could already do an iteration through an array by reference. This gives me a reference. And I can prove to you that this is really a reference by, for instance, doing a print line here. And for instance, here saying let's print the pointer. Let's take the address of numbers 0, something like this. And then here, let's print the address of n, which is just a reference here. And if I run this guy, cargo run, cd iter, and now do cargo run again, you will see that the reference of the first element in numbers and the reference which the iterator gave me here are exactly the same. They are referencing to the same address in memory. So we are really iterating really iterating by reference. That this is really a reference. You could also do a mutable numbers here, and for instance, add another for loop, something like n in, this time let's take a mutable numbers, something like this, and then we can also say star n multiplied by 2, for instance, something like this. And if I run it again, you will see that my values change. So I can iterate by reference or by mutable reference over an array of numbers. This has been possible for quite a while in Rust, and it has been possible in Rust 152 also. And in Rust 153, a few months ago, things changed a lot. We can now iterate by value over arrays. So let me quickly demonstrate that by quitting my Rust Docker container 152 and go to my machine, which runs a newer version of Rust, where I can do nearly exactly the demo as before. I will copy the code, and now a big difference occurs, iterating by value. So here I have opened my, here it is, I have opened my environment. Let me quickly exit from here and do a cargo new iter, something like this. Go into the iter folder and open that one in Visual Studio Code. As I said, this is a newer version of Rust. This is on my local machine, and I will quickly paste in the code that we just wrote. But this time, the big difference is, let me get rid of the mutables here. We don't need that one. I can now change the ampersand here. And that in 153 gives me an iteration by value. I can now simply iterate over the values in the fixed size array. And if I cargo run this guy, you will see that I get the proper values. I don't even have to store that one in a variable. I can put that one directly in the for loop, nothing special here, and it will still work. So this is what really changed in 153. Well, you could ask yourself, are we done? Is that all? Is the talk now over? No, it's not over. It's just the beginning. I wanted to demonstrate to you what's new, and now based on that, we will dive deeper into what's going on behind the scenes. So we will take a look what these iterators really are. We will take a look at the source code in Rust. We will try to re-implement some aspects of iterators on our own to learn more about the inner workings of iterators. And then we will take a look at why it was so difficult for us to offer this seemingly simple functionality. So we will check out so-called Const Generics, and we will check out some breaking changes which the Rust language team had to solve so that this great feature became possible in 153. Okay, so with that, I think we can get started. Okay, I see some first questions coming in Discord. I'm very sorry, I have to quit Discord for now. Oh, I just saw that you asked me to increase the font size. Of course, I will do that. So here, yeah. Thank you very much for pointing that out. Please give me feedback if the font is still too small. The big chunks of code will start from now, so I hope it is not too late. Okay, very good. Nice. So let's dive into the most core abstractions. Oh, so good. Thank you very much. The most core abstractions which are behind iterators. The next part might already be known by those in the audience who already have a very good know-how or a good know-how in Rust and who have already written a decent amount of Rust code, but maybe we have some beginners in the audience for whom this might be new. So, in every programming language, if you want to build something like iterators and helper functions on top of iterators, you need a basic abstraction. You need an abstraction for an iterator. What is an iterator? An iterator allows your code to iterate over a collection of values, read-only, forward-only. So you cannot change the content of the underlying data structure, and you can only go forward. We will see that read-only is not 100% correct here in Rust, but let's say for the sake for now that this is what we understand of an iterator. We iterate, we go through, we walk through in our code the elements of a data structure. And by having an abstraction, we can build helper functions like sum, filter, mapping, minimum values, maximum values, and things like that over all data structures which fulfill these abstractions. So it doesn't matter if you store your data in a vector or an array or anything else, as long as this data structure fulfills the requirements or has the capabilities of the common abstraction, the iterator abstraction, you can always use this generic helper functions like summing, filtering, mapping, and so on your data structure. So what are the most basic abstractions in Rust for iteration? Now, the first one is, let me show you that one here. Let me go into my browser and fire up this link that I've prepared. Is this guy here. This guy, the one, is the into-iterator trait. The into-iterator trait is the most basic trait which allows us to ask an underlying type for an iterator. It only has a single function which is called into-iter, and it will return the iterator. You see it here. Now the iterator is an implementation. This is an implementation here. And as you can see here, self into iter. And the iterator again has to fulfill a second trait, which is the second basic abstraction for iteration in Rust. It is called iterator. So if I follow this link, this will bring us to the iterator trait here. And this iterator iterates over elements of type item, as you can see here, and it has a lot of functions. Luckily, if we implement our own iterators, all these functions starting here are not interesting for us because, as you can see here with these three dots, they have default implementation. The only functionality in this iterator, which is really important, is the next function. This is what we need to implement. If we have a type which should participate in this whole infrastructure of iteration, we need to have an iterator which implements the next function. And this is what I meant with forward-only iteration. There is only a next function. There is no previous function. And all the rest, like counting, summing, and many other functionalities, we get them for free because they sit on the shoulder of this giant here. They are implemented based on the next method. So remember that one. Into iterator is the capability of a type to be asked for an iterator, and the iterator itself is a trait which offers a next function. These are the two implementations. If we want to take a look at the source code I have a deep link in my storybook, which I mentioned at the beginning of my talk. This is, let me zoom in a little bit. This is the into iterator trait in the Rust GitHub repository. As you can see, this guy is pretty old. This abstraction has been there nearly forever. And here you see exactly what we saw in the documentation. We have the type of the items over which we enumerate. In our case, it was an array of numbers, integer 32. So this is the item type, in our case, integer 32, but it can be any type you want. And here you see the implementation of the iterator. You see it, of the iterator trait. If I scroll down a little bit, we see this into iter function, which returns the implementation of the iterator. You see it here. It is the functionality with which I can ask a type, please give me an iterator for you, for this specific type. If you have a Rust vector and you want to iterate over the elements in the vector, you ask the vector by calling this into iter function, and it will give you the implementation of the iterator for a vector that you can use to iterate over its value. And the same is true for every collection type that exists in the Rust universe that implements and wants to play with iterators. So let me quickly go back to our code sample here and change this a little bit, okay? So let me undo that one, take the values here and get rid of that one. Let's put that one into a vector so that we no longer have an array here, just to have something different. And now we can say for number in numbers. You see it? And then we can print line the, number here. This is possible. This in numbers is possible because if we take a look, this is the type vec. So if I go to vec, then I can look up in the documentation that the structure vec implements the into iterator trait. And with that, just because the vector implements into iterator, the Rust language compiler knows that in this for loop, it has to call the into iter functionality to get the iterator, and then uses the calls to the next method to iterate through the elements. And what we get back are elements of type integer 32. This is essentially what's going on behind the scenes. To get a closer understanding, a deeper understanding of all this stuff, let's implement a custom iterator. To be more specific, I would like in my next demo, which will take a while, I would like to implement a generator. A generator is a special form of an iterator where there is no real underlying data structure, but we are generating the values on the fly. I've chosen this sample because I think it's a good way of looking behind the scenes of iterators and understanding what's really going on. Now, for the next demo, I will copy in line by line some prepared lines. And again, I copy these lines from the GitHub page that I showed you at the beginning of my talk. And I will also share this link in the Discord server after my talk so you can take a look at it. Okay, let's get started. First, here, we need a use statement. Let's put that one because we need a random number generator. Next, we need a structure, and this structure will be called passwords. Why did I call it passwords? I called it passwords because I will implement a password generator. It will be a very naive password generator, so it will not generate strong passwords here, but hey, bear with me, it is just for the sake of demoing iterators. It is not the world's best password generator. Now, this password generator has one parameter, which is the length. The length that the user would like the generated passwords to be. Now let's quickly implement this password generator structure, some basic functionality. We will implement a new method which will return by default a password generator which generates passwords of length 10. Okay? And we also implement a helper function which is called withLength. There you can pass in the length and it will give you a password generator with the specified length. You see that here. Okay, so I think I can also get rid of exactly that one. Okay, that looks more idiomatic. Let's put it that way. This still has not really some functionality in it. Of course, we could discuss whether it would be a great idea to implement the default trait here, but that's out of scope for today. We will jump right into the implementation of an iterator. In order to make this passwords a generator, a password generator, we need to implement the Iterator trait that I introduced you to a few minutes ago. So let's implement Iterator for our passwords struct. The type, the item, will be string because we generate passwords and those passwords are of type string. Now, the implementation of the iterator itself will be the passwords iterator, which we'll have to implement in a second. For now, just accept the curly, the red squigglies here. They are fine. We will need to implement this guy in a second. And now we can implement the core method that we mentioned before. We can implement Iter like this. It gets a self here, and it will return the iterator implementation. Okay, here we can return the password iterator, which we will implement in a second. And just for demo purposes, we will pass on the length that the user has chosen for our password generator, just like that. So this is the functionality with which the for loop of Rust can ask our type passwords for an iterator. It will call into iter, and we have to return an implementation of the iterator, which we will have to write now. This was the first step, implementing the Iterator trait. Now let's go on and implement the iterator itself. So let's create the passwords iterator, this one, as a structure. And here we again have our length. Of course, we cannot, as you can see here, use passwords iterator already here because it does not implement the iterator trait. It's not yet an iterator. It doesn't have a next method. So let's write the next method and implement the iterator trait. Import iterator for passwords iterator. The item, we can copy it from here, is still a string. Of course, our generated passwords will be strings, and that's fine like that. Now we have to implement the next method. Let's just implement the missing method here. That looks pretty good. The only thing is this to do, which is not a good idea. We will have to write some code here. Now, let's step back for a second. Now, the red squigglies here are gone because now our passwords iterator is really an iterator and offers a next method. The next method will return the next item optionally. Optionally means that we can always return none if we have reached the end of the iteration. Now, before the system calls the next method the first time, the iterator stands kind of in front of the first element inside of our iteration. And once we call next, we will either get the first element in the iteration in the underlying data structure or generator, or we will get none once we reached the end. In our case, we want to have an iterator which can generate an endless number of passwords. So we will never return none. We will always generate a random new password. Okay, let's do that. Let's first let mute result create a string, and we can already create it with capacity and say we can use the length because we already know how long the string will be because we know the length of the generated password. Now let's write a for loop to generate the letters of the password. For in 0 self length, something like this. This will give us a for loop which iterates through this whole for loop self.length amount of times. Now we can push into some new letters, and here, bear with me, it will not be the best random password generator as I mentioned before. So let's quickly take the byte value of the letter A and add the random thread random number generator generate range a random digit here, and we do that by saying give me 0 to let's take this one, the C value minus the A value, so a value between 0 and 25 including. And this will be this one as char, something like this. So let's see what I did wrong here. This is that one, that looks good. And we have this one, something like this. And we have the random number generator. And at the end, we can return some results, something like this. So let me quickly see what we have here. Undeclared, I thought I used it up here. Oh, of course, I forgot something. In the cargo toml, I need to reference the rand crate, otherwise it will not work. So let me give it a second and cargo build. And which do I have? I think, let me quickly. I will not look for the typo that I did here. So I will just copy in. I see what I did. I don't need to copy anything in. I just forgot to be here. And now it looks good. Now the code compiles. Let me quickly show you again what I do. I allocate a string with a given length, and then I have a for loop, and here I just push in the letter A plus a random number between 0 and 25. I get to 25 by subtracting A from C and convert it to a char. That looks pretty awesome. So now we have the Iterator trait and we have the Iterator trait. So we now have an iterator, in this case a generator, which can generate an endless amount of passwords. And now we can really benefit from the functionality that we get in Rust built on top of the Iterator abstraction. Let me show you what I mean. For pin passwords, this one, new into iter, see that one? And now I say, and this is the important one, take 3. Otherwise, it will run forever. But by specifying take 3, like this one, of course, I need a dot here, not a colon here. Yeah, by specifying the take 3, it is no longer a problem that we generate an endless amount of passwords. The iterator function take, which is built on top of the next function, will stop after calling my next function for 3 times. And here I can simply do a print line. The next password, password is that one, E. Okay, let's run it. Cargo run. Let's see what we get. And we get, oh my God, we get 3 different passwords. 3 different passwords which we can generate through the iterator abstraction by calling into our iter. Scroll up. Iter will generate the passwords iterator. This is the guy here. This implements the iterator method. This implements the next method. And the take 3 will make sure that the next method will only be called for 3 times. This is what I wanted to show you. This is what I wanted to show you so you get an idea of what the core abstractions for iterators in Rust really are. And of course, we can also write it in a different way. I will copy this one in because it is essentially the same, just a little bit in a different notation. You see, again, I can use the with length functionality that we have implemented above and say I want to have 5 letter passwords into iter again, take 3, and then use the for each method to print the next passwords. So if I run this guy now, you will see we have the 10-digit passwords and the 5-digit passwords, exactly what we wanted to have. So the last 10 or 15 minutes, something like this, were primarily for Rust beginners or those who have just used functionalities like this or sum or filter and things like that, but who have never bothered to take a look into the details of how iterators really work. Now you've seen it, and now we have implemented our own custom iterator. So it's a good time to take a breath, because now we are starting in a new sample and we will dive deeper into some more advanced functionalities of iterators and maybe some surprising things, especially for beginners in Rust, surprising things with iterators. And the first topic will be consuming iterators. Let me show you what I mean with that. Let's get rid of this example. Don't need that one. Looks good. And let's do the same thing that I did before. Let's create a vector of some numbers. This time, let's take some Fibonacci stuff. 3, 5, 8, 13, something like this. Looks good. Now let's print the minimum number of this vector. Okay, print line, nothing special here. Okay, the minimum is, use the curly braces, and say numbers dot into iter, this one, dot minimum, and we are sure that there are elements in this array, so this should be fine. Check it out. Let's run this guy, and okay, I don't need the use anymore. Let's get rid of that one. Clear it and run it again. And we'll see the minimum is 1. This is exactly what we expected. What you might not expect if you are a beginner in Rust is this problem. Let's print the minimum 2 times. Oh my God, so many red squigglies just by displaying the minimum number 2 times. Well, the reason for that is the way that into iter really works. So if I go back here, and if we take a look here at into iter, we will see that into iter takes ownership of self. It consumes the underlying data structure. We cannot use numbers after line 3 anymore because it was moved. It was moved into the iterator. And therefore, we cannot iterate twice like this. Of course, there is an easy way to get around that. If we say numbers is no longer the vector itself, but if we just borrow a reference to the vector, so numbers is now a reference to the vector, everything goes away. We have no longer a problem because now the type of into iter is no longer the vector, but a reference to the vector. And now I can run this guy and we will get the minimum successfully twice. This is exactly what we need to do. Note that we did not have to change anything here. Unlike C++, there is no arrow operator like this if we have a pointer. This is how the dispatching of methods work in Rust. It's really a core piece of infrastructure for making ownership work in practice. That even if we have a reference, we can just type in a dot and everything is fine. So again, cargo run, and it simply works. As an alternative, we could also, let's put it that way, use two other functions. Well, I will demonstrate just one of them. I can use the iter function here, something like this, and then everything is okay. You might scratch your head and say, what's iter? We just had into iter. Why now iter? Is iter another trait? No, it's not. The iter function, it's not coming from a trait. It's by convention returning a by reference iterator over the underlying data structure. So this one, this iter, is automatically iterating by reference, and therefore it doesn't take ownership of the underlying vector, and you can call it 2 times. But the behavior is just defined by convention and not by definition of a trait. There is also an iter_mute function, which you can use if you want to have a mutable reference. Okay, this is maybe a little difficult, so I would like to walk you through some additional lines of code, another example, a more elaborate example, where we take a closer look at this into iter and references and iter_mute, because I think, at least it was for me, when I started with all this when to use iter and when to use into iter and what's exactly the difference, this really gave me a lot of headache. And this headache, I would like to spare you this headache, okay, by showing you some simple things. Let's define a struct, because always using just ints is not funny. So let's define a point struct, and let's add some 64 floats here, f64. It is just a very simple point here. Good. Now let's create a vector of points. Let points equals to vector, and here let's say we want to have a point, one, x should be 1.0, y should be 1.0, and then we add a second point, this one, and this will be, I don't care, it's really not important too. So now we have a vector of points. The first one has 1, 1, and the second one has the value 2, 2. So what we can do, if we want to have the first point, let first point, we can say points dot into iter, this one, dot next dot unwrap. This one, and as you can see, the type which we will get back is the point. So in this case, the Rust compiler iterates or makes and calls the into iter with the type of the underlying data structure, which is point. As you can see it here, it is a vector of point. So this is what I get back. I iterate over the points by value. This is what I do here, by value iteration. That is kind of obvious. Now let's change that a little bit. Let's redefine the points here. I'm just shadowing here, so exactly the same points again, but this time I'm going to do it a little bit differently. Let mute iter, we want to have the iterator, and now I will do the following. I will say take the address of points and call into iter, this one. That will give me an iter, which is the implementation of the iterator over point. But now check out what's happening. Let first point, this one, equals to iter.next.unwrap. See what's going on? Now I iterate by reference. Because here, here I have a reference to the vector. Into iter immediately understands, although it's the same call as up here above, it immediately understands that it has to give me an iterator which iterates by reference. So first point is now ampersand point, the reference to point. Very important thing. And this is the magic of Iter. It understands whether you call it directly on the vector or on the reference to the vector, and will give you either the value or the reference which is inside of the vector. And this is where the iter function comes in that I told you before. So instead of writing this guy here, I can say points.iter. See? That is a shortcut for this rather complex syntax here in the back here of this line. So iter by convention, what did I tell you? Iter by convention gives you a by reference iterator over the underlying data structure. So if you definitely want to iterate by reference, call iter and then everything is okay. You don't need to write something like this, which is smart, but kind of difficult to understand. Points.iter is really simple, and now you know what it does. It gives you an iterator by reference. Iteration, something like this. Now we can also do that by, I don't need to that one. I don't need to do that one, of course. Yeah, no mutable here. Yeah, of course, the iterator needs to be mutable. Sorry. It's fine. The mutable thing that I want to demonstrate now, sorry, I just got distracted, comes down in the third demo. Let's redefine the points again. Here, this one. But this time, let's make it mutable. Okay, now we have them mutable. Now, let's define again the iterator. And this time, I will not call points.iter, which we did before immediately here. But this time, I will write iter_mute. And that will give me an iterator over mutable references of the underlying vector. So that would be equivalent to writing ~mute points dot into iter. Okay, that is essentially the same. Just as here above, we could write address of points dot into iter. Now we can say mutable reference of points into iter. That would be exactly the same. So now let's get let first point equals to iter dot next dot unwrap, something like this. And you see, I now get a mutable reference to the point. Let's write it down, okay? Just to make sure that we are absolutely sure what we are doing here. And with that, I can now say first point dot x equals 3.0 and first point dot y equals 4.0, and I can print line something like this and say, give me the first point. And of course, we need the derive debug up here, otherwise it will not work. Let me give that a try, and you see the point has changed. So it worked. We could retrieve by mutable reference iteration here. We got the mutable reference, and then we can change the values in the underlying vector, and I can also maybe print the, it's here, maybe that one is also interesting. And you see, the values also changed inside the vector. It was not just changed here in first point, because obviously this is a mutable reference pointing into the point of the vector. Okay? Okay. I have a question here. The question is, will next return second element or last? Next will, if you call it for the first time, it will give you the first element if there is one. If the collection is empty or the generator cannot generate any values, it will give you none. It is an option, okay? That is important. Once you are at the end and you call next, you will definitely get none, because then it's over. The behavior, by the way, if you call next again once you got none, is not strictly defined. An iterator could decide to start from scratch and start from the beginning and return you the first element in the iterator, for instance. Or the iterator could decide to give you none again. That is defined by the iterator. There is no definite rule for that. I hope I could answer the question with that. Okay, nice. So now I hope you got a better understanding what this into-iter is. You understood that into-iter will give you a by-value iteration or a by-reference iteration or a by-mutable reference iteration depending on the context. Here we have the by-value, here we have the by-reference, here we have the by-mutable reference call. The difference, there is no difference in calling into-iter. Okay, there are multiple implementations of into-iter and the compiler will choose the correct one for you. If you want to make your code a little bit easier to read, then use the iter function if you want to iterate by reference, or the itermute function if you want to iterate by mutable reference. Nice. Breathe in, breathe out, new topic. Let me go into the Rust playground for the next demo here. And the next demo that I would like to show you here is the topic of zero-cost abstractions. Many people ask themselves, oh, sorry, I have to copy it here. I can copy it now. I copied it, and of course, I know. I have to zoom in. So this is a very, very simple loop. And many people ask themselves when working with iterators, okay, how much is the runtime costs? And if you take a look here, we calculate the sum of all values between 0 and 9. So I'm just adding to the sum, and at the end, I print it. Let's run it. And without any surprise, it returns 45. That's okay. But that's not what I'm really interested in. Let's do something else. Let's take a look at the assembler code here. Okay? So if I scroll down and down and down and down and down and down and down, at some point we will reach the main method. Where is it? Where is my main method? If I will not find it immediately, I will look it up. And where is it? Where is it? I have to look it up. Main. Here it is. Without going into any details here, okay, here we call the something like this, and if we take a look somewhere, that's typical. I cannot find my. Here we see it. Okay, here we see it. Here you see playground main. I finally found it. Sorry, it's not so easy for me to read assembler code while demonstrating, so please don't be angry with me. Here you see that we are doing a bunch of move statements and so on, but at the end of the day, you see the call to into-iter, everything is fine, and at the end, we will also see the call to the print functions, nothing special. So we have some runtime costs. Well, not really. If you take a look at what I did, you see I selected debug. And if you select debug and you compile your Rust code, we all know you get pretty slow code, okay? You get pretty slow code and it can be optimized a lot. So bear in mind, this one with debug calls the into-iter and does essentially all the things that I demonstrated to you a few minutes ago. So bear in mind, if we run this guy, come on, run it, the result will be 45. So now let's switch to release and take a look at the assembler code again. Oh my God, I have to scroll through assembler code again. Let's see whether I will find it. Yeah, here it is. And see that one? Isn't that awesome? There is no into-iter anymore. The compiler understood that it can calculate the result during compile time and give me the complete result directly as a constant in the code and immediately called display trait in order to be able to print it on the screen. So that is kind of obvious. You see, it really works. It still works. And it is, oh, sorry, I wanted to run it here. It still works. It works pretty well. And here you see 45, but now there is no into-iter anymore. So this is a kind of very simplified example. I know that, okay? Granted, it's very, very simplified, but it demonstrates the point Zero cost abstractions in Rust mean that when you use iterators, you should not let yourself be fooled by looking at assembler, at generated assembler or LLVM code in debug mode, because there you will see all the overhead of iterators. But once you compile to release, you will see a very different beast. Maybe you don't even see the iterators anymore. It is optimized to a very large extent. And I wanted to make it very clear to you by using this kind of naive example, granted, but still it demonstrates the point. Don't think that iterators, when compiled to release mode, will work as it is in your mental model that you might have in your head. The compiler will optimize it to a large extent, and the assembler code will look very different compared to what you might have, as I said, as a mental model in your mind. Okay? Okay. Good. Nice. Good, good, good. This was zero cost abstractions. So with that, breathe in, breathe out, new topic. Let me quickly take a look at the questions. I think there is one. Okay, here we have a question. Let me quickly read it. Is there any convention how to write code? Let mute variable into iter or let mute variable vector into vector iter mute? I'm not 100% sure if there is a hard best practice here, but I would use the second version. Yeah, I would use the second version. It's easier to read. It's completely clear what is done. It has, for my personal experience, less magic going on behind the scenes. So I would definitely prefer the second version here. Okay, good, nice, good. As I said, breathe in, breathe out, new topic. The next topic and the final topic is, why did it take so long for Rust to enable this thing here, by value iteration for arrays? It is so obvious to write for number in array 1, 2, 3, 4, 5 that it wasn't clear when I started dealing with Rust why this functionality isn't there. So, two things were pretty difficult when building this implementation, and I would like to demonstrate both of them. Okay, let's go back here and start another Docker container. Run this one and run Rust 1.50. Okay, let's run a Docker container with Rust 1.50. Let's create, again, a Rust demo folder, this one, Rust demo. And let's go back to Visual Studio, fire up my remote development tools, and fire up a new Visual Studio connected to my container, which runs Rust 1.50. Okay, oh, I'm in the wrong folder here. So let's go up, oops, up one here and go into Rust demo and open that one. Here we are. Good. Good, here we are. Let's cargo new another demo here and go into the iterator and let's take that one. Good. For the next demo, I am going to write a few lines of code and also copy a few lines of code. Imagine the following situation. We want to implement a trait that tells us whether an array is ordered. It's just for demo purposes. The code doesn't make very much sense, but it's just for demo purposes. So bear with me. I want to demonstrate the problem and what has changed approximately in March this year. Okay? So let's write this trait. Let's call it isOrdered and add a function isOrdered, which returns just a Boolean, nothing special. As I said, the code doesn't make very much sense. There are other traits which you can't use, something like this, but we want to implement an isOrdered for whatever reason, just to understand what's going on behind the scenes. Now, let's try to apply this isOrdered trait to an array. So down here, we will say let ordered equals to, or let numbers This is what I wanted to say. This one, 1, 2, 3, 4. That's fine. And then let's print whether, oops, sorry, print whether numbers is ordered. Okay, something like this. Obviously, this doesn't work because the trait is ordered is not implemented on an array of 4 elements of type integer 32. So what we have to do is we have to implement. We have to implement the is ordered trait for an array of t. So we need here a type here. But the problem is that, as you might already know, that an array in Rust has a fixed size. So we have to specify the size. Let's do that. So we want to implement it for an array of size 2. We have to specify a size. It is necessary here. And then in order to be able to implement it, let's say this has to be ordered and copy. Okay, something like this. So the content has to implement the ord trait, which gives us a nice compare function, and it has to implement the copy trait in order to be able to copy the elements from the array. So let's implement the isOrdered functions, something like this. And let's quickly write a few lines of code to have this done. It's pretty simple. First, let's say if this one, if the self length, this one, is 0 or 1, by convention, we say then, return true, then the collection is ordered, then the array is ordered. Okay. Essentially, we don't really need that one because we have the length here. But bear with me, we will need this code in a second. For now, just accept it, it's okay. Then we iterate over the elements in our array. Not difficult. Let mute preferences. Previous is none. And then say for item in self. Note that our item is a reference to t because this is how iteration in Rust prior to 143 really works. If some item is lower than previous, and we can say return false. Otherwise, we just advance the previous one by saying some item. And at the end, if we manage to go through all the elements, we know that there is no item which is smaller than the previous, so we know it's ordered ascending. So this might be a naive implementation of check whether our array is ordered. See it here? Okay, good. That looks pretty awesome. And with that, we should be able, we should be able to call isOrdered. And yes, as it happens, it now works. It works perfectly fine, and we can try it. Cargo run. Again, cargo run. Yes, it's ordered. And if we mess up, let's see. Cargo run, false. And that looks very nice. But what happens if I add another digit here? Everything breaks. Because here, as you can see, this doesn't work. This doesn't work because this has a constant size. So I would need to copy this guy here and implement it again for the size 5. Of course, this doesn't make any sense, but now at least the code compiles. It works for 5. What would you do if you have an old version of Rust? You would probably write a macro. This has been done for you, so you don't need to write it yourself. But you would write a macro in order to generate implementations for this nice little trait for arrays of different sizes. That is not a good idea. So what we essentially need is let's get rid of this guy here because it's so ugly. What we essentially need is we need here this one as a parameter. And this is what we call Const Generics. So what we essentially would need, we would need to be able to say this is n And n, as you can see here, is a constant number of type useSize. This is what we want to do. And this came in Rust 1.51 and was a very, very important precondition for implementing by-value iterations over arrays. So let me prove to you that this really works. Let's take that one and let's forget about this old stuff in Rust 150 or so, and let's replace this guy here with a new version of Rust. And you see, the error is gone. It now works. This feature is called Const Generics, and it came with Rust 151 in March 2021. So this was an important step towards the simple feature of being able to write for number in array 1, 2, 3, 4, 5. We needed Const Generics, and it came with Rust 1.51. So now you also learned what Const Generics are, and maybe you weren't looking at this Rust feature before, and now you got some additional knowledge of Rust out of this demo, not just about iterators. Okay, very good. There I have a question. The question is, it's just vec of t because a vec doesn't have a fixed amount of elements. Exactly correct. That is exactly correct, and that is why you do not need Const Generics for vectors. And that is why iteration worked very much earlier for vectors than it did for arrays, because arrays have a fixed size. Okay, good. Oh, thank you, Ono, for pointing out that I missed a bracket in the print line statement. I found it myself, luckily, but thank you for pointing it out. Okay. Now, why didn't this by-value iterator over const arrays come with Rust 151? Because we got Const Generics. So why didn't we get it immediately? Why did we have to wait for another 2 versions until 153 to get this feature? Well, for that, we have to understand that implementing into Iterator for const generic arrays would have broken a lot of code. And I would like to demonstrate to you so you understand what was the problem. It's a kind of history lesson because now it just works, but by learning this history lesson, you hopefully get some deeper understanding in how method dispatching works in Rust and so on. And yeah, maybe it's just interesting. I hope so. So let's write and copy a little bit of code. So let's get rid of that one. And I see I already spent an hour, and I announced that this talk will be an hour, so I will copy a little bit more of the code and not write all this code. So yeah, this is just a history lesson, but hopefully an interesting one. Let's define our own data structure. Let's call it myArray. Obviously, it's not an array. It's a useless structure because it contains only a single element of type phantom data. If you are not familiar with phantom data is what it says it is. It is just a phantom data item. It has size 0. It goes away when you compile this code to release. It doesn't exist. It is just a placeholder. Any underlying data structure will be here. And I call it myArray because I implement a data structure, myArray. Please use your imagination. MyArray is some fancy own array and it has some fancy inside data structure. We really don't care. This is not the point here. We also do not want to use the Iterator trait that Rust has built in. We implement our own Iterator. This is exactly a copy of the Iterator trait that I have demonstrated to you at the beginning of this talk. So we'll not go into any further details because this is our old friend Iterator and you already know what this does. Same is true for the Iterator trait that Rust has built in. I want to have my own one. I want to have my own iterator, and I called it myIterator. Again, it's a copy of the Iterator trait from Rust, just to be able to play with it, okay? So I'm fine with that one. Now, in the early days of Rust, the iterator for arrays were implemented based on references. Let me show you that one. This is an implementation of into iterator and then also the iterator itself by reference. You see that one? This exists for a pretty long time. It is there since 1.0, yeah, and it was added with Const Generics in Rust 1.51. So the into iterator trait for references to arrays worked for a pretty long time. So we can add this implementation of the into iterator trait for references to my array in our own simple example here. So let's do that. This is old code. This is just a simulation of what was there before we had Rust 153. So here you have the reference to the array. And of course, we also need the iterator. Let's do that. Iterator, again, just the phantom data. We don't care about the implementation behind the scenes. We just care about the data types. And this is the implementation of the iterator, in my case, my iterator. And in this case, again, it's about references to T. So this is a reference iteration. Okay? Are we good? So let's try this guy. Let's try this guy by creating this one here, some instance of my array. And then we call into iter. This is not a reference. My array is not a reference. ARR is not a reference, but still, because there is only a my into iterator based on references, Rust will automatically pick the by reference iterator and will give you an item of type reference to integer 32. So although we don't have a reference here, we get a reference iterator because this is how Rust works. This is how Rust method dispatching works. I could easily change that one, to a reference and everything would still be fine. Nothing changes. But I can also leave that out and the system will automatically recognize, okay, there is only an implementation for the reference here, so we are good. Remember, this implementation has been here for quite a while, so this code might exist. People might have built code that relied on the fact that calling this into iter gives me a reference and not a value. So what happens? What happens if we implement a by value implementation for into iterator and iterator? Let's do that. I've prepared this code. Copy it. Boom. Sorry. Should be not here. Should be here. Let's copy the my into iter. Again, this is by value. And let's copy the iterator. You see, this is not a reference. Just like up here, this is a value. And guess what? Just by adding the capability of doing by value iteration, we broke existing code. Because now the into iter thinks it should take the by value iterator up here because this here is not a reference, but it is a value. So if I add the reference here, everything is fine again, because now the system knows I want to iterate by a reference. But if it is like that, just by adding implementations here, by adding implementations for traits, we break existing code. And that was the big problem. The Rust team, the Rust compiler team would have broken a lot of existing code by just implementing a by value iterator for arrays. And that obviously was not acceptable. So there had to be a different solution. And luckily, there was. There is now in Rust a trick, and I want to show you this trick in the last demo that I will do today. Okay, let's get rid of this example. You can find this example in my demo repository. And I would like to copy, let's see, here, this little bit of code and walk you through it. It's nothing new. It's just things which we, this one, it's just things that we have done before. Okay. And I want to use the std, here it was, the std back into it. Now this is good. This is nothing special. It's just what we did before, but I need to have this few lines of code to demonstrate the point. You see, the first one is a vector. We had that before, and we use iter to iterate by value. You see, value. Here I have a reference to a vector. We call iter, and we get a reference to the elements inside the vector. This is how vectors have been working since the dawn of time, okay? Now let's try exactly the same with an array. This one is, as you can see it here, no reference. We call iter, just like here, no reference. We call iter. And for vector, we got an I32 a value, not a reference. But you see what's going on here? In arrays, we still get a reference. And this is what the trick of Rust is. In Rust 153, the compiler recognizes exactly that scenario where you call iter and changes the behavior to be backward compatible. So in contrast to the vector, we get a reference and not a value. But we also get a warning that this will break. In the upcoming version of Rust, in the Rust 2021, this will break. So it is okay to break this functionality in a major version of Rust, but it was not okay to break it in a minor version. In a minor release of Rust, this was not okay. So therefore, they did this trick. So if you do that one, the array will behave differently from the vector. Of course, if you want to explicitly call into iter, you can do that by using this syntax here. It's essentially exactly the same as we had before, but only different syntax. And for this syntax, the Rust compiler will not do the trick, and you will get a value and not a reference. So this already new behavior, no warning. This trick to be backward compatible in the future, this will break, and in the future, this will give us an I32 and not a reference. And because we finally got the implementation of Iterator and Iterator by value, all the fuss that I did and talked about in the last hour was done in order to enable exactly that one. See? For I in array, and we do no longer, for arrays, get a reference, we get a value. And just this syntax is already there, it stays there for backwards compatibility. This is what I wanted to show you. I wanted to give you a closer understanding of what's going on behind the scenes. And I hope it was interesting for you. Let me quickly summarize. We started with this one. I showed you what's new. Then we dive deeper into what iterators really are. I showed you some interesting behaviors of iterators, like consuming iterators, like mutable references, by value iteration, and reference iteration. And then we used this knowledge to understand why it took so long for us to learn this trick that I showed you, value iterations over arrays. And with all this information, I hope you had an interesting hour together.